In lesson 9, we're going to talk about formal charge. It's very quick, very simple, very easy. We use it as kind of a bookkeeping method to look at individual atoms. So I'm going to circle oxygen in kind of his only space here. Okay, we're going to add up the number of bonds and the number of electrons. We're going to compare it to what we expect. Oxygen up here is number 6 in his valence energy level, right? His level 2 energy level here. He should have 6 electrons surrounding oxygen. But you notice we have 2, 4, 6 plus 1 bond is 7. So he's going to have a -1 formal charge. That's what this minus means here. And conversely, sulfur, also number 6 in his valence group, but he has 3 bonds, 1, 2, 3, and 2 electrons here, 4, 5. That's not enough. That's why he's showing a positive formal charge here on this dimethyl sulfoxide group. But what about this carbon? Carbon's number 4 in his energy level. He should have 4 valence electrons, 1, 2, 3, 4 bonds, and no extra electrons. That's perfect. He is neutral. And same for the hydrogen. It only needs 1 electron. It has 1 bond. Let's take a look at what that means. Here's a picture of dimethyl sulfoxide. Make it less abstract for us here. Let's bring it over here. Once you take a look here at the sulfur in the middle, quite positively charged. Quite positively charged. And the oxygen over here, highly electronegative. So when we look at what we call formal charge, which is really just an accounting system for where my negative and positive poles may be in the molecule, we get an idea of where the dipole moment might be. And of course, the dipole moment is going to be positive here and negative here. So we should see kind of that magnet direction like that. And sure enough, if we look at the picture again real quick here, I don't know why I made it go away so fast. That in this picture is depicted here. The positive and negative is along this side. So when it comes to acids and bases, we're going to be looking at where things are extra positive or extra negative and why. We're going to want to be able to predict where things react. So that's formal charge. Let's use another example. Have a look at diazomethane. This is a well-known molecule, super explosive, by the way. It's a super simple, they call it a diazo compound. And maybe we don't really need to get into that, but names are always cool. A diazo group is just 2 linked nitrogen atoms at the end of something. And this is as simple as it gets. Diazo, meaning 2 nitrogens. Diazo. That's it. So now that we've totally talked about something unimportant there, let's look at the formal charge on this. Nitrogen should be 5, should have 5 valence electrons according to the second energy level, group number 5 there. And this nitrogen here, I mean, he's got 6, he's got 2 bonds, and he's got 4 valence electrons, so he's going to be a -1 formal charge over here. And this nitrogen over here in the middle only has 4 bonds, so that's a +1 formal charge on him. +1. He doesn't have enough electrons. So what you see is an electronegativity that goes this way. There's the arrow we draw for the dipole, right? It shows exactly which direction the electrons are interested in traveling, where you're going to find them. So you would expect an electron cloud to look something like this. Heavy red on this side, super electronegative on this side. And you notice the methyl group here is going to be neutral. Carbon has 4 bonds. It wants to have 4 bonds, so that's all good. Yeah? You get it. Okay, let's look at another one. Let's get a couple more examples in. How about acetonitrile oxide? Now we're having some fun. Oh, we don't need to get into the naming conventions for everything, but let's just take a quick peek at the formal charges. Oxygen here. What's oxygen supposed to be at? He is number 6 on our periodic table here in group number 2. Well, what do we see? 2, 4, 6 electrons and a bond. So that's too many. That's going to give him a -1 formal charge here. -1 on the oxygen. How about the nitrogen? Nitrogen has 4 bonds and no spare electrons. That's not enough, so he's going to have a plus. So once again, we see a positive and a negative here. Our dipole is going to look like this on this side, right? Pardon my angle there. Maybe I don't want to confuse you. Try and get a little closer here. So once again, we're going to see that this electronegativity is at like the terminal end, is what they call that, way out here. And that's going to make this highly reactive. It's going to make it very easy for anything that wants electrons to attack from so many directions. And you really want to look at the geometry of this and think about, like, if I want to take electrons from something, which is going to be a big part of making new molecules and reacting chemicals, how easy is it to reach here? There's nothing to protect this oxygen from its greedy, greedy nature. Especially when this nitrogen's already hyperpositive. Yeah, so these are going to be connected by that positive-negative relationship, but you have so much space out here to attack these electrons with. You're going to see it happen. How about this carbon? 4 bonds. Carbon's number 4 in this group right here. He's happy. That's neutral. And same here with this carbon here, 4 bonds. Carbon always wants 4 bonds. You've got that down by now. Should we look at another example? Here's a really interesting one, methyl isocyanide. Cyanide meaning a triple bond between a carbon and a nitrogen. Cyanide. Cyanide, think about it for a minute. Carbon and nitrogen. Methyl, of course, being the methyl group. Okay, let's do our formal charges. That's what we're looking at here. Well, this carbon has 3 bonds and 2 electrons. That's 5. And carbon's only supposed to have 4, so that's a -1 formal charge here. Versus this nitrogen group. Look at the nitrogen group. 4 bonds and no spare electrons. That's a +1. So once again, we have a plus and a minus, which is going to create a dipole here like this at a terminal end. So again, we see this openness to electron attack from all directions. We'll talk about that more in later lessons, but look at all the geometry. Any angle can be approached here. And any kind of molecule or atom that wants to come by looking to strip electrons, like say I float an oxygen over here, that oxygen is going to rob carbon at gunpoint. I promise you. They don't mess around. Oxygen, like I've talked about, very greedy for electrons. And I can tell you that this methyl isocyanide is a very important thing. It's used in a lot of stuff. It's also thought about as being used to prepare, like, most of the ideas on the beginning of life come from this kind of a molecule. This is a really important molecule. So just notice here that when you have this plus and minus formal charge at a terminal end like this, you're going to see electrons want to, like, really be around out here. And that makes it very reactive. So formal charge teaches us how and why of this. Just look at these atoms individually and count up the number of bonds and the number of electrons around that atom itself. This carbon here, of course, is neutral, just 4 bonds, right? And you will have an idea of where the electronegativity in the entire cloud of the molecule is. It's not the same everywhere, right? It's local. It's local. And in our case, these examples that I picked are all on one end like this. And I really enjoy showing this off to you because you can see just how many ways a molecule could come in and attack this carbon. And that's exactly why it's so violently reactive. It's explosive. A sample of this is exploded when heated in a sealed glass container at cold temperatures. It doesn't get safer than that. 1 drop of liquid, according to a diary I read, 1 drop fell back into a dry flask and exploded the flask. 1 drop. Okay, so if you're ever Breaking Bad, just remember methyl isocyanide. Do not mess around with this kind of molecule.